Welcome to Calc 3. This is section 14.2 on vector fields. So the idea of vector fields is that vector fields show movement potential for functions. So for example, on the left we have two different vector fields, A and B here. So if I think about a function here and I start at a particular point, the vector fields give me kind of an idea of how that function may increase in time. So if I start here, in the point in the red here, I see it kind of expels out from the origin. If I start here in the point on the lower one, I see I kind of move in a circle. This is kind of a velocity vector. This shows how different points may go along the curve. So I can see direction of rotation. I can see how things might have different rotational points in space, how they might be sinks or sources, and different potential movement for functions. So we define a vector field with a capital letter F to be a function of 2 or 3 or many variables. So here capital F is a function of m, n, and p, where m, n, and p are functions themselves of x, y, and z. So we take an input location, we input our location, and we output a velocity. So a vector field's a function whose domain takes in particular functions, giving a location, and outputs a vector that gives a direction of movement. So recall from earlier in the semester that the del operator is the vector operator of partial derivatives. We used it when we did gradients of surfaces, when we took the partial derivative of surfaces. And so the del operator is a vector, the partial x, partial y, partial z. So we define divergence to be a measure of the compressibility of a vector field. So we define divergence of F to be the del dot the vector field. So we can say this is the partial with respect to x of the first component of F plus the partial with respect to y of the first component, of the, if we think of F as the m component, we can think of it as the x component, and the partial with respect to y of F in the y component, plus the partial with respect to y of F in the z component. So in your text, it does reference this as mx plus ny plus pz, where m, n, and p are the entries in the F, in the vector field, in each of those components as shown up here, m, n, and p. Curl is a measure of rotational action, and that's where we use the cross product, where we cross the vector del cross x. So this in vector notation is partial x, partial y, partial z, crossed with the vector m, n, and p, where those are each vector locations. We could think of this as our typical cross product, I, j, k, and we have our vector of partials, partial x, partial y, partial z, and we have m, n, and p. So your textbook does give some shorthand notations for this. In particular, if we have a two-dimensional vector field in 2D, we do see that we have nx minus my as our curl of F. So that's a quick shorthand notation. So let's do an example here where we're finding the divergence and curl for this vector field. So the divergence of the vector field, let's do that first. So divergence of F. So this is the partial derivative of x with respect to the vector field negative y, plus the partial derivative of y with respect to the second component. And so this gives us a partial derivative with respect to x of negative y squared is 0, plus the partial derivative with respect to y of x is 0. So we get 0. This is an idea that we call incompressible. The field is incompressible. We cannot compress this field. We can't make this field any smaller. Now, if we have the curl of F, we can use this idea of nx minus my. We can also think of this in IJK notation, if you don't want to remember these little tricks, you can think of partial partial x, partial partial y, partial partial z. We have negative y squared, x, and we can always add on a dimension to be 0. And so taking the cross product of these particular vectors, we get 0 and 0. So 0 minus 0 for the first entry in the curl. And then our second entry, the partial with respect to x is 0, partial with respect to z of negative y squared, so 0 minus 0. And then we get the partial with respect to x of x is 1. The partial with respect to y of negative y squared is minus 2y, but we tack on the negative, so we get 1 minus 2y. So that becomes 1 plus 2y. So this is our curl of f. So we curl out into the z direction into our vector. So let's define our potential function. So if we have a vector field that is the gradient of some scalar valued function, so if this is true, where the vector field can be written as a gradient of a surface or a scalar value function, then we call phi, this symbol here is called phi or phi, it's called the potential function. Note in your text, in the ApexCalculus text, the phi is written as lowercase f. I choose to write it as phi because lowercase f is used in surfaces from earlier in the section. So oftentimes the potential function in other resources is notated with a phi. So if we know that f is equal to gradient of phi, if we want to find the potential function, if we know a gradient, so phi sub x, given that we know a vector field, if we know the partial derivative of phi with respect to x is a component of a vector field, is the first component, and the partial derivative of phi with respect to y is the second component, we can integrate both sides. So we get the integral of phi with respect to x. Move this over. So phi has to be equal to integrating both sides, 2x plus y dx. And phi also has to be equal to the integral of 2y plus x dy. These statements both have to be true if phi is a potential function, because this is partial phi x and this has to be partial phi y, because the gradient of phi has to be the vector field. So when we integrate this, phi has to be equal to 2x squared plus xy plus some function, let's call it g of y, because if I took the derivative with respect to x, that function would be 0. This becomes 2y squared. I'm sorry, I dropped the 2, so this should be over 2 plus x y plus some function h of x. So now we play the matching game. Plus g of y, and this becomes y squared plus xy plus h of x. So these two functions have to be equal. So those pieces are equal. So we've used both those pieces. X squared matches up with the h of x, and g of y squared matches up with the y. So in both pieces, our phi has to be equal to x squared plus xy plus y squared plus some integration constant, which we typically assume is 0. So this is our potential function here. So the next video will have several short problems that talk about the gradient and curl for this, for these functions. If you have any questions, as always, feel free to let me know.